Hello everyone, I'm James Wilson. Nice to see you again. Last time I did this problem here. I worked on this circuit and I found the state space equations. This time we're going to find the transfer function of this circuit using the impedance method, right? So for some basics, first of all, notice that we have two input sources in this circuit and one output. That means our transfer function will be in this form. Y of s is equal to g1 of s, g2 of s times the input u. Notice that because this is a 1 by 2 vector and this is a 2 by 1, that the result will be as a scalar. Since we have two inputs and we have a circuit, the tip here is to use the superposition property from circuits. So what that means is, as we can see from these circuits here, is that we find a g1 of s and g2 of s independently from each other by assuming u1 can operate independently from u of 2 and vice versa, and finding the transfer function components one at a time. This basically breaks the problem down into two different smaller ones. A little review of the Laplace transforms here. The Laplace transform of the voltage of a capacitor is equal to 1 over c times s. And the Laplace transform of the voltage of an inductor is simply L of s. Now that we have that out of the way, because we're using the superposition property, the first thing I want to do is find g1 of s, which we know is equal to y1 of s over u1 of s. So the tip here is to assume that u2 is an open circuit, right? So now we just have one input. So this greatly reduces the size of the problem. So the first thing that we want to do is write down the exact equation for y1. We know that y1 is the sum of the voltages across these two components, right? This will be VL1, this will be VR2. Suppose we have current I going in this direction. We know the voltages of these two items here. Excuse me, let me write this down first. Y1 of s is equal to VL1 plus VR2. But using Ohm's law for impedance, right? V is equal to I times Z, right? We can also write this as I times the sum of the impedances, L1 of S and R2, right? So now the question is, how do we find this I? Well, if you look here, you just have a voltage source, U1, and one single loop. That means we can find I quite easily. I is equal to U1 divided by the total impedance, which is equal to U1 over, grouping like terms together, R1 plus R2 plus the two capacitances, 1 over S, 1 over C1 plus 1 over C2 plus the inductance, L1 of S. That's pretty straightforward. If we normalize this a little bit here, we get, let's see here, U1 over L1 S squared plus R1 plus R2 S plus 1 over C1 plus 1 over C2 times S. Now, if we substitute this into here, we get y1 hat of S is equal to I times this quantity. Writing that out, we get L1s plus R2 over, times S, over L1s S squared plus R1 plus R2 S plus 1 over C1 plus 1 over C2 U1 of S, which is equal to Y hat S, which is equal to G hat S U hat S, right? So what does this mean? This means this quantity is G1 of S. So we found our first item. Okay? So I just cleared some space. I just want to point out an error in my original drawing. This is supposed to be a current source, and the first part of the video is a voltage source. But that's okay because I drew it correctly down here. So here's our G1 of S. Now we wish to find G2 of S. Starting similarly from before, we know that Y2 of S is equal to the sum of these two voltages, VL1 and VR2, which I'll write more clearly here. We also know from before this is equal to I, let's call this loop here, we'll call this I2, and we will call this I1. This is equal to I2 times the sum of the two impedances, L1S plus R2. Okay? So now the trick is, how do we find I2? Now, a convenient thing we can write here at this node is Kirchhoff's current law. The sum of the currents must be equal to 0. Taking direction into account, we have U2 of S minus I1 minus I2 is equal to 0. Conveniently, we can use the node voltage method and easily determine these currents. So if I call this V1 and define my ground down here, we can rewrite this as U2 is equal to V1 over S times R1 S over 1, V1S over R1S plus 1 over C1 plus V1S over L1S squared plus R2S plus 1 over C2. So what did I do? I took V1 and divided by the impedance on the right side to get I2. And I did the same thing on the left side here on this loop to get I1. Please don't panic that I skipped some algebraic steps. I just multiplied each term by S over S to write the equations in standard form. So at this point, all we need to do is solve for V1. Right, so V1, again, for time reasons, I'll be skipping some algebraic steps, but solving this out, we get V1 is equal to U2 times, in the denominator, L1S squared s cubed, apologies, plus r1 plus r2 s squared plus 1 over c1 plus 1 over c2 s. In the numerator, we have r1 s plus 1 over c1 times L1 s squared plus rs, r2s, plus 1 over c2. Right? Now we have v1. We have our equation for I2 over here. Substituting v1 into this equation, we get I2. Right? I2 is equal to, now if you notice, when we multiply v1 in, wait, what? Pause. Sorry about that. We notice that when we substitute v1 into the equation for I2, that this and this will cancel out. This simplifies our expression to be, in the denominator, L1 s cubed plus r1 plus r2 s squared plus 1 over c1 plus 1 over c2 s. And in the numerator, we simply have r1s plus 1 over c1 times s, right? So now with our I2, we can finally find our solution, which means y2 of s is equal to I2 times L1s plus R2. This ends up being equal to rs squared plus 1 over c1 s over L1 s cubed plus r1 plus r2 s squared plus 1 over c1 plus 1 over c2 s times u2 hat of s, which, by the way, this is g2 of s. Right? So our transfer function is up here. We have found g1 of s. We have also found g2 of s. Simply substituting it into that vector there will give you your final transfer function y hat of s. Thank you. Hope you learned something from this.